much. Hello, everyone. My name is Vik Krishnamurthy. I work on the research team here at Snorkel AI. My research interests are broadly computer vision and multimodal learning. It is my immense pleasure to announce Peilin Yu today for our AI guest speaker series. Peilin will be talking about Alfred, which is the first system for programmatic weak supervision that creates training data for machine learning by prompting. So without any further ado, Peilin, please go ahead. Stage is yours.
So, hello everyone. Thank you for joining us today. I'm very excited to introduce you to Alfred, our first attempt at a prototype system to synergize the capabilities of foundation models and programmatic weak supervision. Alfred is the first prototype system of a next generation of programmatic weak supervision system. And this work has appeared at ACL 2023 last year as a system demonstration paper. So in short, the goal of Alfred is to better distill information from powerful foundation models to annotate textual or image data. For today's talk, I will structure the talk into four main parts. First, I will provide a brief overview and background on prompted weak supervision. Then, I will introduce the key design choices of Alfred. Next, I showcase some code snippets from a real Alfred workflow. Finally, I will discuss some potential future directions for Alfred. Let's begin by diving into the background of the prompted weak supervision. Machine learning applications heavily rely on large-scale label data across various fields. Label data serves as a foundation for machine learning algorithms to recognize patterns, make predictions, and perform complex tasks. Traditionally, people have relied on crowdsourcing for data annotations, either through in-house experts or via online platforms such as Mechanical Turk. Crowdsourcing requires human annotators manually going through each data point and label them. And this process can be highly time-consuming and sometimes impractical due to data regulations. Additionally, domain-specific data, such as legal or financial data, often requires specialized expertise, which further add on to the cost. In the recent decade, programmatic weak supervision, pioneered and advocated by the folks at Snorkel, has offered a very efficient alternative to manual crowdsourcing. So instead of asking human experts to label each data point, experts will write down heuristics or labeling functions in code. These heuristics can range from regular expressions for text or to distant supervision sources from existing knowledge bases, or even weak classifiers. While these high-level labeling functions can be extremely noisy, this is acceptable and manageable within the programmatic weak supervision framework. So given the unlabeled data, we will first acquire the votes from those expert curated labeling functions. Next, we will pass the votes into a probabilistic label model that are capable of learning from the agreements and disagreements within the votes, all without access to any ground truth labels. And the label model estimates a probabilistic label or a distribution over the label space for every data point. These probabilistic labels can then be used to train an end model, typically a neural network classifier, such as BERT or Roberta for text, or ConvNet vision transformers for images. The resulting end model are typically small in scale and can be easily deployed or served. So to better understand this process, let's look at a concrete task. Imagine you want to build a sentiment classifier that can react to financial news headlines and classify them into neutral, positive, or negative. And you have collected a bunch of financial news headlines. Like any data science project, we start by examining the unlabeled data points to understand it better. So very quickly, we notice that the headlines mentioning price target going up or down, like raised, this can serve as a good heuristic. So we'll write a labeling function with a regular expression that tries to match this pattern. So, but what about all the synonyms and phrases commonly used by financial news reporters? I can say price tag raised, upgraded, going up. To build this comprehensive regular expression that actually express our heuristics can be very hard. I don't really have a CFA, nor do I know how to use the specialized language in financial reporting. So I will only have to try my best and gauge which words might be relevant. Even with exhausting out possible synonyms, we might still miss some coverage. Like this example, the order is changed. To match these heuristics better, we have to change our regular expression. Notice here, a simple order change can make our labeling function totally fail. And for programmatic weak supervision, we have to design a collection of high-quality labeling functions in order to tag this dataset. The issue here is, despite we having all those good heuristics, we cannot seem to find an easy way to express them accurately. So one way to get around this is to ask foundation models for help. So in recent years, transformer-based foundation models have revolutionized many general tasks across vision and language domains, especially thanks to their flexible language-based interfaces. Building on this progress, researchers are now exploring how foundation models can address challenges in weak supervision. And one promising approach that synergizes these two fields is prompted weak supervision. This technique, first introduced by Smith et al. In their work at Snorkel, utilizes natural language prompts to guide data annotations and have shown promising preliminary results. So by leveraging the capability of foundation models and the efficiency of programmatic weak supervision, prompted weak supervision offers a powerful solution for data annotation challenges. The key innovation here is the shift from writing rigid code to define heuristics as weak labelers with natural language prompts. These prompts, known as prompted labeling functions, instruct the model to provide heuristic answers. And the results from those prompted labeling functions are then going to combine using the label model to produce a set of probabilistic labels then to be used to train an end model. This new approach simplifies the data annotations process by using natural language prompts, making it much more accessible and enabling a broader range of users to engage in effective data annotation. So going back to our example, now we can simply ask a model to answer our question in three languages. And we finally don't have to worry about all the synonyms of price target going up. Let's now look at three more examples of prompted labeling functions. Say if we're going to build a news classification dataset and we want the mention of President Biden to vote for politics news. We can write the expression down like this, trying to match all the variation of mentions of President Biden. With prompted labeling function, we can simply ask the model, is there any mentions in the text? For the second example, we will want to understand if a given text expresses certain positive sentiment by matching a set of pre-compiled list of tokens that is associated with positive sentiment. To achieve this, we have to build this collection beforehand. With prompted labeling functions, we can simply do this by asking a question with the model. For the third example, we consider an animal image labeling task, where we use visual attribute stripe to vote for the class tiger and zebra. Previously, we would have to first collect supervised training data for attributes classifiers like stripes, then train a classifier to make the decision. But now, with modern vision language models like Clip, Bleep, Florence, etc., we can simply express these attribute decision tasks as prompts. So one intuitive question to ask is, why not just prompt the model for labels directly, as the models are so powerful now? It turns out this is not contradictory to the heuristic-based approach, as label prompts are precisely one type of heuristics in the prompted weak supervision paradigm. In the prompted weak supervision setup, zero-shot labeling prompts are complementary to all the other heuristics. In our Alfred paper, we demonstrate two tasks. We actually gain an average of 8.7 performance by integrating a variety of heuristics, including the zero-shot labeling prompts. So foundation models in the loops are great. They offer powerful capabilities and advanced performance. However, they come with significant challenges. They are computationally demanding, and manage multiple models with heterogeneous interfaces can be complex. And all those foundation models also come in various scales, Some likely through APIs, some can be hosted in your laptop, but some needs to be self-hosted in a GPU cluster. So to use them effectively in a human-in-the-loop workflow, as in any data science project, we need a more streamlined approach. So this is where Alfred comes in. But wait, why do we need another LLM wrapper to achieve this? The motivation of Alfred actually arises from our earlier experiences with programmatic weak supervision, such as the open source Snorkel framework. As the developers and data scientists, we will meticulously work with the Jupyter notebook, writing down and iterating on top of our labeling functions to reach high quality. And now with foundation model in the loop, we really need to nail down the right abstraction to make the interfaces as lean as possible while maintaining the flexibility we enjoyed and loved from earlier programmatic weak supervision frameworks like Snorkel. So this motivates us to build Alfred, a prototype framework that defines interaction interface with the right abstraction for the next generation of foundation model in the loop data workflow. Alfred features optimized inference throughput, smooth local development experiences that facilitates prototyping, and support for language and vision language models for multimodal annotation tasks. So let's look at Alfred's critical design and features in more details. So shown here is a full workflow of Alfred system. It may seem like a lot, but let me walk you through it step by step. So starting out, we'll begin inspect the data and try to understand the data. Then the developer can start writing down informative heuristics as prompt templates. When applied to datasets, the template will automatically generate typed query objects. So in this code snippet, we show a string template object that defines a prompt template for text data. In the main field, the placeholder for the ad hoc data instances are defined within this template. And by specifying the answer choices, the potential answers of the model responses are restricted. And by applying this template to a given data instance, it generates a typed query object. In this case, it's a rank query object with the candidate options for the model to choose from. Alfred also supports multimodal templates, like the image template that can generate queries for both contrastive or autoregressive vision language models. The second feature for Alfred is a typed query and response feature. So through our project experiences, we identified two main language interaction modes with foundation models. It's ranking and free completion. So the respective query and response type are defined accordingly as completion queries that corresponds to a completion response, and rank query will correspond to a ranked response. So for free completion, we'll only need to pass a completion query to the model client, and it will give us the prediction content as the main payload. As for rank query, it's going to yield a ranked response with the top one candidate, along with the normalized probabilistic scores for each aggregate candidate tokens. Then, to finish this loop, the responses need to be parsed and translated into a numeric vote by an Alfred voter. The Alfred voter also supports calibration that are able to mitigate potential biases from the foundation models. Now, let's look at a few more code snippets to better understand this. To define a voter, you'll begin with a label map, which will parse the model responses and map them into a numerical vote. As for the exact matching, we want to match the response, in this case, to the key of the label map within the model responses. So the matching function here can be fully customized. Here, we only want to ask if the key for the label map is in the response, but you can replace it with any fuzzy matching mechanism, such as embedding similarity matchings or semantic similarity thresholding. So finally, by applying the voter to the model responses, we can acquire the numerical votes. So to close the loop, we need to discuss how Alfred hosts the models. Starting out, Alfred supports the latest frontier models that are typically hosted via API endpoints. Alfred supports models from AI21, Anthropic, Cohere, Google, and the accelerated inference framework ROC, and GPTs from OpenAI. Users can quickly launch a client and interact with it only with a line. As for local hosting, Alfred offers local model capabilities for Hugging Face Transformers model accelerated inference engines like VOOM, Onyx, or Flexion. Similar to the API-based models, we have a uniform and standardized interface for you to launch the model. A critical feature for Alfred is the support for remote model hosting over clusters or cloud. Alfred uses gRPC for client remote interactions while maintaining all the local functionalities. Reader can launch an Alfred server in the cloud and interact with it with a local client that connects to it. All the functionalities will remain the same. Model hosting, especially in universities, sometimes happens in managed clusters with various credential support. Alfred implements a custom port forwarder that supports multi-factor authentication or private key access. Another critical feature for Alfred is dynamic batching. So when hosting the model locally, either with a server or client, Alfred will automatically bucket queries with similar lengths to reduce the impact of useless paddings on throughput. So when tested with the 11 billion T0++ model with V100, dynamic batching can give us a 2.9 times throughput increase. Alfred also caches query and responses with SQLite on both client and servers. This will reduce redundant queries to the model and enhance efficiencies. Additionally, it allows developers to inspect the results much faster with the same interface. And with contrastive multi-modal models such as Clip, Alfred will actually caches the encoded representations for each modality. And this will significantly enhance the throughput by reducing redundant encoding operations. So now we have covered the main workflow for prompted labeling function development. Next important piece for Alfred is a workflow for label modeling, where we will actually turn the noisy votes from the models to labels. So Alfred implements a standardized interfaces for 4 types of common label models: major vote label model, naive Bayes label model, and flying squid, which features a triplet method-based optimization method, and noisy partial label model, which supports voters that can vote for multiple labels among your label spaces. In the code snippet here, it's a simple majority vote label model, but Alfred also can extend support to many more label models. Then the estimate label can be used to train and serve an end model. We have described the core design decisions of Alfred. So let's look at more concrete examples to better illustrate the workflow. So let's go back to our financial sentiment classification example. Starting out, we need to set up an Alfred client. In this case, we want to launch a Llama 3 AB model with VOOM as a backend. Now, we need to start templating or writing down your prompt instructions. In this case, it's a raw string, which then to be wrapped by our string template. By specifying the answer choices, we're restricting the possible candidate generated by the model. And then we'll define a corresponding voter, which is gonna parse the candidate and translate them into a numerical vote, where in this case, -1 means abstention. And the matching function here is the exact match. Finally, after acquire a bunch of templates and voters, we can go through the samples and use this interaction mechanism with the Alfred client to acquire the votes. With a naive-based label model, we can acquire the probabilistic labels from it, then simply pack it into a training data loader object within PyTorch, and train your favorite end model, in this case, Roberta, with it. So now we have covered a simple workflow. Let's jump into the discussions. So running in-house data annotation over frontier models have numerous advantages, but they also bring along data privacy concerns. In a lot of cases, we don't want to share our data across the internet. We believe that prompted with supervision and Alfred offer a viable alternative to running locally hosted open source model that achieve similar performances compared to cutting-edge models that are hosted via APIs. So with Alfred, we achieve a 98.5 filtering rate on toxic prompts with Llama 2 7B, compared to GPT-4's 97.6%. This is measured with the do not answer benchmark dataset, which is used to evaluate safeguarding mechanisms in large language model systems. So this demonstrates us that we can enhance open source models to potentially match or even surpass frontier models through APIs. The second point is, despite the growing range of large language models and multimodal foundation models, in today's modern software stacks, there is still a need for a wide range of narrow models. For example, even within the large language model systems, you may require small intent classifiers for AI safety, or classifiers that tries to identify potential IP infringement. And you need to create data for them. I see Alfred and prompted weak supervision as a very much capable potential building block for this future. So Alfred is our first step in exploring the importance of language in human data model interaction. We anticipate a lot more automation to be built within this interaction model. Currently, Alfred only uses foundation models at a very utilitarian scale. But foundation models have the capability to fundamentally transform the landscape. And with language at its core, I hope these models can act as the gears that connect and potentially drive many more production-grade software. And I have been very excited to see progress recently from the field. So in summary, to address the computation challenges and to provide a standardized framework for weak supervision researchers and users, we introduced Alfred, the first prototype system of a second generation of programmatic weak supervision. So Alfred features optimized inference throughput, a smooth local development experience with standardized interfaces that facilitates fast prototyping, and compatibility with vision language models to support multimodal annotation tasks. So here I will end our talk right here, and thanks for joining us today. And let's open the floor for some questions.
I've actually had a question regarding the image classification part. I was wondering if you can explain with a bit more how we can do how Alfred would support something like a basic image classification workflow. Because I think you showed financial sentiment, right?
Yes.
Or sentiment classification. Mm-hmm.
So right now, the search sample is a typical attribute-based classification labeling function. So showing on the right here, the prompt labeling function is suitable for contrasting models like CLIP, where we actually offer multiple prompts as candidates. So when passed to the CLIP model, it's going to give us ranking choices among the candidate prompts. So we can parse its preference into a vote to the label. And by having multiple prompt labeling function in this fashion, we can combine them regardless of raw data types, and just go through the programmatic expression workflow to gain a privacy estimation of the labels. So the key thing here for image data is the decision to use which type of foundation models. So for CLIP models, contrasting-like models, you have to structure it as a rank query. And for autoregressive models, it's going to be something like an open completion, or you give it candidates to do it. So it's all supported within the image template mechanism. So it's really up to the users to choose what kind of mode that you wish to do. But for image data, typically, you probably want to start with some label prompts, either in contrasted fashions where you supply it with an image template that generates rank queries, or you just do the open completion with a autoregressive vision language model like Blade or Florence.
Okay, thanks. And then the other question I had actually was with regards to the caching. So in this case, you would cache every single text prompt that you get, and every single kind of image prompt that you would get, so that you can retrieve it faster.
Yes. Well, it's actually a user based heuristics, because we don't want to overflood our memories or disk with caches. So to starting out, the user can set the maximum caching sizes for their applications. But by default, we do cache everything.
Hi, Peilin. Thanks for your presentation. I had two questions. One was on when we're creating these prompt functions, you're presenting the answer choices. And there's been recent work that shows that the order matters in how the answers, how the language models return responses. Is this do you also like perturb the answer choices, or is that something the user needs to do, like present the answer choices in a different order to maybe get like an unbiased answer?
So to clarify here, once you generate the answer choices, the default way we would use those rank queries to the model is to score the candidates. So it's regardless of the orders. It's like we are calculating the conditional probability of those two aggregate tokens based on the questions. So in this case, it wouldn't matter. But let's say when we're running it through the API-based models where the endpoint doesn't support us to score the token candidates, the way we would achieve it, or it's implemented, like for the OpenAI model, is where we would provide the answers as part of the prompt and let the model choose it. And that's when, like you said, the order might matter. And it's up to the user to define the context. And we see that as an orthogonal part to the system. But like typically when people want to use this functionality, answer choices, we would just score them using a local model. And that's going to be agnostic to the orders.
And then another question, just empirically, what have you found useful in building, this weak supervision model? Are more models for, say, a prompt better, or I'm trying to think, like, if I were to develop this a weak supervision model, like what is the best way to get like a high accurate model from it? Do we need like multiple models giving, multiple labels, of course, right? Like how many of these help in a high quality like solution? If you have any empirical like results or thoughts on that.
Thank you. That's another excellent question. I would say like any data science framework, it's going to be up to the task you're working with. But typically, we would see benefits by running even the same heuristics through multiple models, just to sort of aggregate their biases. But the thing we see here is by transforming rigid code to languages, it sort of free us from expressing certain expertise. For example, if you have a pre-trained model that is specialized on financial data, then for non-experts like me, I can say something in plain language. I can state the prompt in plain language, but somehow the model can help me contextualize the problem and help me answer it better. So again, I would say from an empirical perspective, yes, it's helpful to run through multiple models, but a lot of advantages from transforming code-based labeling functions to prompts is that you can use, you can rely on model's capability to express a supervision in a sort of a vaguer way, liberating you from having to think of all the possible matches.
We also had a question from Chang Ho. He's asking, I was wondering if template or prompt elef generation part can be automated or assisted by LLMs. Do you have any insights regarding this?
That's an excellent question. That's actually going back to the prospect part. When I talked about how this version of Alfred only uses large language models at a very utilitarian scale. Because like in this system, a lot of pipelines are connected by data scientists or developers. But in fact, through this workflow, a lot of stuff can be grounded to languages. For example, the heuristic we think about how they transform into an instruction template for models. So yes, I do believe a lot of automation can happen, not just from the templating stage, but for data filtering, data preparations, and how this human and foundation model in the loop system can give feedback to the developers. So yes, I believe automation in the templating and other parts of the Alfred system would be sort of immediate next step. Yes.
Peilin, thank you so much for this wonderful talk and the wonderful presentation. All our attendees, thank you so much for attending.